So what I'm going to talk about today is an introduction to MIRISim and give an example use case. So for the introduction, I'm going to motivate MIRISim, why we decided to make it, talk about how we decided to make it, and how you can install and use it. And then for the example use case, I'm going to use the specific science example of ERS project 1288, which is looking at feedback from massive stars in photon-dominated regions. This talk itself will be available later, and so the links that I've got in the top right here are clickable to the MIRISim user guide and the science overview paper. So jumping right in, the motivation to create MIRISim, this is really twofold. Selfishly, it came about because we want to use it for commissioning. But there's the added bonus of also getting the community ready to understand what they're going to get from MIRI. So this using MIRISim and the JWST pipeline gets you ready for the deluge of data that we're hoping to get next year and to test your data processing techniques and analyses ahead of that deluge. It also helps you get sciencing so you can compare the predictions from theoretical models that have been put through radiative transfer codes to what you would expect to get from MIRI itself. So with MIRISim, really, you can just hit the ground running when the data starts to come in. So what is MIRISim? It's a Python 3 package, which incorporates our best understanding of MIRI at the current time. So all of the distortions and transformations that go through the instrument, efficiencies, the dispersions for the spectrometers, noise sources, cosmic rays, all of that kind of stuff has been incorporated into MIRISim. And the way we've done this is by using MIRI's what we call calibration data products. So our understanding of the instrument. These are also the products that we deliver to Space Telescope that are then put into their calibration reference data systems, CRDS, and that's what's used to inform the pipeline. Okay, so this is using the same data models that go into the pipeline are put into MIRISim so that we can make sure that we're incorporating our best understanding of MIRI as it currently stands, of what the on-orbit performance will be. MIRISim simulates most of the MIRI observing modes, so it does imaging, and you can see the imaging filters towards the top right of the screen here. It does the low-resolution spectrometer, which you can see at the bottom left, and the medium-resolution spectrometer, the IFU on MIRI, which you can see in the middle of the screen. What it doesn't do is coronography, but all of the other modes are captured in MIRISim. So the modes that we do capture are shown here in red, orange, and blue. And the reason I'm showing this plot is to remind you that the MRS, LRS, and imager field all cover slightly different parts of the sky. And so when you're setting up a simulation, that needs to be taken into account. And the reason I mention that specifically is because we do have a scene generator, or an SkySim is the module of MIRISim that allows you to populate a scene on the sky full of sources for MIRISim to observe. So we've got spatial specifications of point sources and extended objects, as well as spectral specifications where you can set up a spectral energy distribution, use library SEDs, throw in spectral lines, or indeed use text files with lines in spectral energy distribution or FITS files themselves as inputs to generate what MIRISim should simulate observe. And I'm showing two examples of how to set that up here. In black is a terminal showing the default sky simulation configuration file or INI file, and I'll come back to these INI files in a little bit. And then all the way on the right, I'm showing a Jupyter notebook where we go through setting up such a scene, which is available in the user guide. So how do we get and install MIRISim? So I've got a link to the MIRISim website on the next slide, but basically it's installed via an installation script at the command line. So it creates its own Anaconda environment to make sure that you've got all of the right dependencies ready to go so you can get MIRISim running fairly straightforwardly. And so anytime you run MIRISim, you'll have to remember to activate that MIRISim Anaconda environment. It's been tested on both Linux and Mac OS. I do know of 1 or 2 people who've tried using it on Windows. They haven't complained yet, but we haven't done that thorough testing. So there are 3 different ways of using MIRISim: directly at the command line, within Python, or within a Jupyter notebook. Generally, we try to keep MIRISim and the pipeline compatible with each other, but sometimes one will get updated and the other won't because our timescales aren't always aligned. So it is recommended to run MIRISim in a separate Anaconda environment from the pipeline. And that is described more on the web page at the bottom of the screen. So getting started, what I'm showing here on the right is a screen capture of very basic first thing you should probably do with MIRISim, which is generate the default configuration files. And that will generate 10 files, 5 of which are important, the other 5 of which are direct copies but have more documentation in them. So this sets up your simulation, your scene, and your simulator configuration files, or .ini files. And you can use those at the command line. You can also use those within Python or in a Jupyter notebook. Also available as part of the user guide is a number of walkthroughs. The example that I'm showing here is how to use the LRS in slitted mode. Jupyter notebooks that show you how to go through MIRISim, all available in the user guide. And here's a little bit more information of how to set up your simulation. So you want to specify all of the MIRI parameters. You can do that in your ini file, although if you're going to do anything looped, for instance, running MRS simulations, I would recommend doing it within Python because it makes it easier to loop through the settings. You can also extract MIRI observations from an APT file. It will only use one scene, and so that's what I meant earlier with showing you that the MRS, LRS, and Imager have different fields of view, so you have to make sure that your scene covers everything that you need. Using the apt.run facility will simulate all of the MIRI observations in the APT file and output everything to subdirectories based on the observation name. And note that if that folder exists, that simulation is just skipped. Okay, so it's not overwriting itself. 2 primary input files that I've already talked about is setting up the observing scene and also setting up the instrument. The outputs of MIRISim, on the other hand, can either be 2 or 3 files. We have an illumination model, which is an internal MIRISim product, which basically gives you an idea of how the detectors are being illuminated. And the detector image is the final output of MIRISim. This has all of the exposures and integrations and cosmic rays and all of that taken into account. And that's what is referred to as level 1B data. So this is the data that's pipeline ready. Now, if you're running an MRS observation, there's also an output FITS file of a 3D cube that shows you what your scene looked like. Because if I go and show you the outputs of MIRISim here on this screen, you can see the bottom 2 images are the illumination model on the right and the detector image on the left. So neither of those are easily parsable into a sky cube. Okay, so that's one of the reasons why we provide that extra check on whether you think your scene was set up properly. So these are the 3 types of output from an MRS observation. At the top right, you've got a sky cube. So that gives you your MRS alpha and beta directions. So those are those map to the V2, V3 focal plane coordinates of web. The illumination model you can see in the bottom right is the traces of the dispersion that have happened to that data, and the gray lines in between show you the mapping of those dispersions. On the left, I'm showing that the final detector image. This is what's ready to be put through the JWST pipeline. So a very quick example based on MRS observations of the Orion bar. So this is a simulation that was provided by one of the co-PIs of the PDRs for all ERS group. So there is an input FITS cube. You can see an example spectrum here and some of the slices of that cube at different wavelengths to show that the emission varies across the field. On the left here, I'm showing the output, bottom left, I'm showing the output sky cube with a version of that same slice from the initial input FITS for reference. In the middle, I'm showing the illumination model, and what you can really see in this, hopefully you can see my mouse, but towards the bottom right of that middle panel, you can see a lot of dots. That's one of the spectral lines coming through in the traces from the spectrometer. And then finally, the large picture on the right is showing the detector image, the final output of MIRISim. So how do we get more practice with MIRISim? I highly recommend going to the MIRISim Science Examples GitHub repository. There's a lot of Jupyter notebooks there with specific science cases explained and simulated through the various MIRI light paths. And of course, there's the demonstration directly following this talk. Any troubleshooting that we've seen so far, sometimes the calibration data product website goes down. We're still trying to figure out why and when that happens. But that might cause your if you don't have the right CDPs downloaded, that might cause your MIRISim simulation to fail. If you get any kind of FTP or SFTP error in your simulation, delete your CDPs and re-download them. And here I'm just also listing the APT and pipeline versions that we've tested the most recent MIRISim version against. So just to quickly summarize, talked about why we started up MIRISim to give a sense of the on-orbit performance of MIRI. We've built it in Python 3 and it runs in its own Anaconda environment. There's instructions on the installation page on how to get it, which is an installation via command line scripts. Talked a little bit about how to use it and what the outputs are